thing that is in here. You don't need to know anything that's not in here, and you need to solve a problem. You will. There it is. That's exactly what you're going to get. You're going to get your chemical shares for proton and NMR. You're going to get your approximate chemical shares for carbon and NMR, the approximate frequencies or wave numbers for your IR. Okay. Now details like, for example, yeah, here's your carbon bond, whatever, but specifically carbonyl versus carbon-carbon, specifically carbonyls, what is an ethyl, what's an amide, what's ketone or aldehyde. Those are but the broad things that we. Okay. So, just a review from last time, we started looking at heterocycles. So, first of all, we said what's aromatic. To be aromatic, you need to have a cycle. You need to have a continuous array of p orbitals, meaning all your atoms in that cycle need to be sp2 hybridized. And then, if that is the case, and you have 4n plus 2 electrons, that is aromatic. If you have only 4n electrons, that is anti-aromatic. The word non-aromatic only applies to when you don't have a continuous array of p orbitals in a cycle. So it could refer to an open chain. It could refer to a cycle that doesn't have a continuous array of p orbitals, any of them. Okay? Now, if you have a heteroatom, then you need to consider if that heteroatom has pi electrons that are making it aromatic. Now, it doesn't matter where I put the electrons, whether they are inside or outside the ring. That is my drawing whim at the point in time. It doesn't tell you anything about whether those electrons are part of your aromatic pi electrons or not. Pay no attention to where those electrons are drawn. I certainly don't make it mean anything. But when you look at this, if each of these atoms is going to be sp2, which you needed to have a flat molecule, and typically we're going to make the assumption, I'm going to ask you questions like, assuming planarity, are these aromatic and aromatic, not aromatic? You have all of these being sp2, all of these having a perpendicular p orbital. But if they're sp2, then they have 3 sp2 orbitals, right? The typical sp2 has 3 sp2 orbitals and a perpendicular p orbital. So what that means is that these 2 electrons right here are in an sp2 orbital. These 2 electrons are forming this pi bond. These 2 electrons are forming this pi bond. and these two electrons are forming this pi bond. And of course, electrons are not localized like that, but this is a continuous array of the orbitals, so the 6 pi electrons are free to be localized. But these two have nothing to do with that. They're perpendicular to the array of p orbitals. So those two electrons are available to attack, for example, hydrogen ion. So this molecule, in the presence of hydrogen ion, will pick up potentially a hydrogen, become positively charged, and not alter the fact that the ring is still aromatic, because we have not in any way, shape, or form changed the pi electrons that make this ring aromatic. Yes?
I have a question. When you have molecules that have multiple ends inside of them, and you ask like which one is basic or acidic, are you saying specifically which one is basic or which one is acidic or is it?
No. I never asked you whether it's acidic. If you have a nitrogen with 2 electrons, it's either basic or not.
Okay.
To be acidic, you need to have a proton that somebody's going to come and take away. So the question is, can that nitrogen attack a proton or not? But I'm not never saying that nitrogen is a proton. So is it a basic or not? That is the question. In this case, this is basic because it can pick up a proton without messing up the aromaticity.
What if you had another end?
But if you have, let me finish. I'm trying to answer your question. Really trying. Okay. So, if you have instead something like this, I'm just going to put it outside because I know otherwise you're not going to pay attention. In order for this to be aromatic, which it is, I need to have 6 pi electrons, which involves these two, this one, this one, this one, and this one, to give me the 6 pi electrons that I need for this to be aromatic. The thing that is perpendicular is this hydrogen. I don't have perpendicular electrons like I have in here that can attack and are not part of my aromatic ring. These two electrons are part of this aromatic ring. So I cannot use them to attack hydrogen because if I use them, I will become non-aromatic. Okay? So this is aromatic as is, but if somehow this were to attack a hydrogen, then this would become non-aromatic because this nitrogen would then become sp3, we don't have a perpendicular p orbital, and now we only have this end where the electrons can be delocalized. So this is not going to happen. This nitrogen is not basic because if I use it as a base, then my aromatic ring now becomes non-aromatic, which means we're going up in energy, which means this is not likely to happen. So, in a molecule, if you have a nitrogen double bond with a pair of electrons, this is basic. If you have a nitrogen with a hydrogen and a couple of single bonds, this is non-basic. It always works out that way. Okay? So when you look at molecules like this, this nitrogen has a double bond, this is basic. Double bond, this is basic. This is basic, this is not basic. This is basic, this is basic, this is basic, this is not basic. Any one of the basic ones could attack H+, become positively charged and not disrupt the aromaticity. But the NH cannot and will not attack H+. Yes?
If it was instead of NH-OH, would that also be an okay?
The analysis is the same, except that with an oxygen or with a sulfur, in NH, you only have one pair of electrons. So is that pair of electrons part of the aromatic ring or not? And when you have oxygen or sulfur, you have two pairs of electrons. So one of them is part of the aromatic ring, and the other one is on the perpendicular p orbital, sp2 orbital, that can attack H+. Same in here. This is part of my aromatic ring, while the other one is in my perpendicular sp2 orbital and is free to attack H+. So for oxygen and sulfur, they can act as bases while remaining aromatic, while in nitrogen, it's either or. Either you're part of the aromatic ring or you're available to attack. Okay? All right, so, and here they're showing you, right? These two are tied up here. These two are in here, available to attack H+. I am not saying the two on the inside of the ring mean they're part of the aromatic thing. I could draw them out here or anywhere I want. It is still, these two are going to be on your p orbital part of the aromatic ring, and that makes a nitrogen non-basic. Are we clear on? Okay.
It's not attached to the axis with you, like on which one is basic or non-basic.
Right. So, first of all, on the first problem, you're being asked, classify each of these compounds as aromatic, anti-aromatic, non-aromatic. Assume planarity. Assume that if possible, this thing is going to be flat. And then decide whether these are one of these. How about the one on the left?
That's aromatic. Not maybe anti-aromatic. That's H.
So, first of all, to even deserve the word aromatic or anti-aromatic, I need a cycle where all the atoms are sp2 hybridized, so they all have this perpendicular p orbital, and all the p orbitals need to be parallel. That's why I say assume planarity. And then, if I have 4n pi electrons, right? 4 times, in this case, n would be 2, 8. Then this is anti-aromatic. But only all of those things are true. Again, if I had shown you this, and ask you, is this aromatic, anti-aromatic, or non-aromatic? What would be your answer?
Non-aromatic.
None. Because there's an sp3 carbon here, we don't have a continuous array of p orbitals. This is non-aromatic. Now, if I showed you this, and I asked, is this aromatic, anti-aromatic, or non-aromatic? What would you say? It is anti-aromatic, because now with this positive charge, I have a carbocation, I have a continuous array of p orbitals, but I only have 4 pi electrons. So this would be anti-aromatic. Whereas if I show you this, and I add aromatic and aromatic and non-aromatic. Aromatic, because I have an array of continuous p orbitals with 6 pi electrons, right? 4n plus 2, this is aromatic. Is that clear? Okay. Okay, this one, aromatic. We have 6 pi electrons in a ring with continuous p orbitals. This is aromatic. And this one would be non-aromatic because these are sp2 carbons. We don't have a continuous array of p orbitals. And then let's say I told you for each of these nitrogens, decide for each nitrogen whether they are basic or non-basic. But this basic. This one, non-basic. And this one. The ones that are basic is because the electrons are not tied up in maintaining aromaticity, while these 2 electrons are tied up in making this ring or this 2 rings aromatic. We have all atoms in here sp2. We have a continuous array of p orbitals. And how many pi electrons? 10 pi electrons. That is 4 times 2, 8 plus 2, 10. This is aromatic. Okay, so if we have a bunch of benzene rings, that is an aromatic compound. Now, the more benzene rings you put, the more bigger this cloud of electrons becomes, and the more easy it is to self-destruct things at various places. So it is possible for larger molecules to do some chemistry that you wouldn't be able to do in benzene. But let's for now not worry about this. I'm not going to ask you questions about this. We're going to assume that for aromatic compounds, we're not going to do a simple addition of HBr and be able to carry out that addition. Certain molecules again, like tryptophan, this is an aromatic ring, or this is an aromatic ring over here, like this indole moiety is very common. Lots of heterocyclic compounds like this. Okay, now, of course, benzene is aromatic, very stable, which means it survives long periods of time. In petroleum, a lot of petroleum compounds contain benzene, and benzene-derived compounds. And we use a lot of the petroleum compounds to make a lot of drugs that contain benzene. Yet another thing, why it's such a bad idea to be burning fossil fuels. Because in addition to the stupidity of burning them and releasing carbon dioxide and increasing global warming, when we have alternatives like solar energy and stuff like that, it's the basic concept that we make a lot of plastics and a good chunk of our drugs from petroleum. And we are essentially burning away the raw material that we're going to need to make that. So how do you make a hospital work? Every instrument that you use has plastic. Every drug that you inject is also being derived from petroleum. And we have to be forget away. But no, regardless, I know. We are amazing in our stupidity. So, because a lot and lots and lots of compounds contain benzene, we come up with unique names for them. They are repeated over and over again. So when you have a benzene ring with an OH, this is called a phenol. So compounds that have this, the base name is phenol. And then you may have, some substituents, and you'll say blah, 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 phenol. Blah, 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 toluene. Blah, 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 aniline. Or anisole. These are common names that you're going to run into in lab and whatnot. This carbon directly attached to the benzene ring is what we call the benzylic carbon. So on the benzylic carbon we have an aldehyde, that's benzaldehyde. On the benzylic carbon we have a carboxylic acid, that's benzoic acid. On the benzylic carbon we would have a nitrile, right? That would be benznitrile, something like that. Okay, so it is because this is your benzylic carbon that we call these molecules like that. This is acetophenone, styrene, whatever. These are some of the common names, and you're going to see those on and on. Now, potentially. Benzene, and only benzene, because it is such a common substrate. We have a lot of substituted benzenes. So, and a lot of 1,2 substituted benzenes. So, if and you can draw your benzene like this, you can of course draw it like that, alternating double and single bonds, or you can just put a ring here to indicate that they're localized by electrons. If you have substituents in carbons 1 and 2, you could say 1, 2, blah, 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 benzene. Or you could say ortho, blah, 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 benzene. 1, 2 substitution on benzene, not on cyclohexane, not anything else, but on benzene is ortho substitution. 1, 3 substitution is meta, and 1, 4 substitution is para. And you could say ortho whatever, para, meta whatever, para whatever. Okay, so you're going to see that very, very frequently. So I could say like orthomethylphenol. Okay, so the methyl and the OH and the phenol are ortho, that type of thing. So I could call this ortho-dibromobenzene or 1,2-dibromobenzene, or para-nitrophenol, where this moiety over here would be your phenol, and the nitro is para to that OH. Or I could call it 4-nitrophenol or something like that. So if you are drawing meta-bromoanisole, your anisole would be this. Meta would be 1,3 substitution. Bromo, that would be your meta-bromoanisole. Your toluene is this. Para is 1,4 substitution. Nitro group is NO2. That would be your para-nitro toluene. While it's certainly possible to have more than 2 substituents, on which point in time we usually just name all the visual substituents of the benzene ring. So this would be 1,3,5-trinitrobenzene. Or you could use this as a base phenol, where this would be then carbon number 1. And then say 2, 3, 5, 2, 4, 2, 4, 6 trinitrophenol or something like that. While I'm going to hold you responsible for things like anisole or aniline or phenol, because they're way too common not to know, monosubstituted special names, you're not responsible for these disubstituted special names. Yes, we can talk about crystals or whatever, nobody will. Realistically. So don't worry about the disubstituted special names. But the monosubstituted, a phenol, you need to know what it is. Okay. And I could look at, let's say this, and say this is anisole. I could look at this as an ether that has 2 substituents attached to the oxygen and say this is, now as a substituent, a benzene ring, we call it a phenyl substituent. Right? So this could be phenyl, methyl ether. Or I could look at this and say this is a substituent of my benzene ring. And then call this something like methoxybenzene. So there's all kinds of ways that I could name this. But understand that you can talk about a substituent on your benzene ring, and assuming the benzene is the parent compound, and then talk about the substituent. So I could talk about, let's say, a halide, and talk about having this being a substituent of the bromide, and call it phenobromide. Or I could talk about this being a substituent of the bromide. This with the CH2 is called a benzoyl bromide. Or I could talk about bromobenzene. Or I could talk about bromo, or I could talk about methyl phenyl ether, or the other variations that I told you. Anyway, as a substituent, this is a phenyl substituent, this is a benzoyl substituent. So if you're using those as substituents, learn the difference. Benzoyl includes a CH2, phenyl is just a benzoyl as substituents. Of course, if you're talking about an aromatic ring, we have your CC stretch at 1600, the overtones, and then of course the hydrogen sp2 carbon stretch at about 3100. Okay. Proton NMR, they're going to come between 7 and 7.5 ppm. Carbon NMR between 120 and 150. As usual, we don't pay attention to mass spectrometry, but of course something like this would be incredibly stable because this resonance all over the place. So that would likely be the base ether. As usual, we don't pay attention. UV, just like NMR, shows overtones for benzene. So that's easy also to see on UV. Okay, we're done with 16. So let's do the last chapter before the exam, which is chapter 17. So in chapter 17, we're going to do some synthesis. So A benzene ring is aromatic. Disrupting this aromaticity ain't trivial. So, if I had a simple carbon double bond carbon, if I have this molecule, right, and I put HBr, I would end up adding hydrogen and bromine across the double bond. That's what we call an addition reaction. And I carefully made this symmetrical so I don't have to worry about my chemical order. Okay, now if I have a benzene ring, so here let me put these on a more specific example. So let's put in here Br2. I would have an addition reaction. If I put a benzene ring and Br2, there is no addition reaction. None, it just lasts at the end. Because these electrons are tied in the aromatic ring and they don't want to disrupt the aromaticity. If I make this a much stronger reagent, which will involve mixing Br2 with a strong Lewis catalyst, where these two will first react together and effectively make bromonium ions, a super electrophile. Now, we might be able to budge the benzene. But only when you add that Lewis acid catalyst to have these two react first and form a really, really reactive electrophile.
So you put a UV light where the radical is not strong enough? Like that?
There's no radicals.
Oh.
I'll go through the mechanism. But we're still not going to have an addition reaction. The reaction that we're going to have is going to be a substitution reaction, where instead of this hydrogen at the end of the day, I end up with a bromine. We are substituting this hydrogen for a bromine. We still have the aromatic ring at the end of the day. We have not converted my double bond to a single bond. I have not added two bromines. I have substituted a hydrogen with a bromine. So it's a very different type of reaction. Okay, so this type of reaction here is called an electrophilic aromatic substitution. And we're going to see 5 different examples of it. One of them is my halogenation. So if I have a benzene ring, if I add a halogen, so this could be chlorine, bromine, presumably iodine, and a Lewis catalyst, either ferric bromide or aluminum trichloride, you're going to end up introducing X in here. We'll go through the mechanism. 2, you're going to have your benzene ring, put a mixture of nitric and sulfuric acid. The combination of these two effectively forms X plus. The combination of these two effectively forms NO2 plus, a nitronium ion. And then your nitronium ion reacts, and we're going to substitute that hydrogen for NO2 and form nitric rings. 3, we're going to mix this with fuming sulfuric acid. None of these are nice reactions. These are very, very high energy, very nasty reagents, very potentially, explosive and harmful and corrosive and all of the good stuff. Because you don't get your benzene to react otherwise. then we form this sulfonic acid. Or we're going to do a Friedel-Crafts ACE alkylation first. So an alkyl halide reacts with Lewis catalyst, like aluminum trichloride, effectively form this really reactive carbocation, which then will allow you to alkylate. Or a Friedel-Crafts acylation, where I'm going to add an acyl chloride as opposed to an alkyl chloride in the presence of a Lewis catalyst. These two are going to react together and effectively form an acylium ion. And that is the reactive species that then will react with benzene and form this type of acylated benzene. So those are the 5 types of electrophilic aromatic substitution that we're going to look at. All of these are going to involve my benzene acting as the nucleophile and this extremely reactive electrophile. So let's start with halogenation. So remember, my reagents are going to involve a halogen, a Lewis catalyst, aluminum trichloride, ferric trichloride, tribromide, whatever. Aluminum is in group 3A, has 3 valence electrons. Iron, same deal. In this situation, this can form 3 single covalent bonds, but only has a set of electrons. So it would very much like to have an octet. It's electron deficient. That is an electron fire. Okay. Now, so these 2 electrons here are going to form a covalent bond to aluminum. This being my nucleophile, this being my electrophile. When we do that, this chlorine is not positive, and this aluminum is not negative. Right? Which, there's 2 ways that you can view this. You can either view this like this, and then say, oh, here's my benzene, and these 2 electrons are then going to attack this chlorine to break this bond and give electrons to the positive chlorine that desperately wants them. Or you can look at it like this and say, hey, this thing is so desperate anyway that this is going to break, and we will directly form chloronium ion and this thing over here. And this is the species that we're going to attack, regardless of how you look at it. We have a really, really electrophilic chlorine, one that is strong enough of an electrophile to budge the benzene to break its aromaticity. But it's only going to be temporary. So let's assume my benzene attacks, and your benzene attacks, and now we have disrupted the aromaticity, which means one of these these two electrons form a bond with chlorine, and this piece is now left with a positive charge. This benzene, right, we're not drawing this, but this had hydrogen, 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 hydrogen. So those hydrogens are still here. But this benzene is desperate to re-aromatize. And at this point in time, this hydrogen is about the most acidic hydrogen in the world. Anything floating around, we'll call it a base, but it could be in any molecule. Can extract this hydrogen, put these two electrons back in here, and give you back your aromatic ring. And now we have done my substitution reaction. Okay. So this right here is a reactive intermediate. We call it the sigma complex, something like that. But recognize that it's very short-lived, and there's an incredibly strong drive to re-aromatize the ring, abstract that hydrogen, and give you back your benzene. But that is effectively how this happens, but only because we have a super electrophile. Yeah.
Why is the hydrogen so acidic right there?
Because I have a positive charge here. If I abstract this and put these two electrons here, I go back to having an aromatic ring. What makes a stronger acid a more stable conjugate base? And there's few things that are more stable than a benzene ring. So forming a benzene ring where you didn't have one before is an incredibly driving force. Okay? So, for all of these reactions, regardless of what the super electrophile is, you are going to have your benzene ring leaving nucleophile attack the super electrophile, form this sigma complex, which will then immediately go on to re-aromatize the ring and will give you a substitution reaction. We're effectively substituting this hydrogen, if you want to think about it, for chlorine. Okay.
So it'll never be that bottom hydrogen that gets taken, that bottom proton?
How is that going to do anything for this positive charge? Or for re-aromatizing the ring? If I take this hydrogen, I'm going to end up with two electrons here. No, it's this one that will re-aromatize the ring. All right, so okay, so we have an aromatic ring, all my 6 p orbitals naturally overlapping, and a continuous array of p orbitals with 6 pi electrons aromatic. We attack a super electrophile, break temporarily the aromaticity, create an sp3 carbon, but very quickly we are going to re-aromatize, and we're going to end up with a substitution reaction. Of course, you could write resonance structures trying to show, whatever, but effectively, the sigma complex is less stable than a benzene ring, and the driving force is to re-aromatize it. Halogeneity, these are the 5 different reactions we're going to look at. So you need a strong Lewis acid like ferric bromide or aluminum trichloride. Form this type of intermediate. You can view it this way, or you can view it just breaking this bond and forming just this type of intermediate. Probably this is more realistic but if you can visualize how you have more elastic charges, it's actually what. So this attack formed by sigma complex, then a base comes in, and we're going to re-aromatize and end up with bromolyl. Okay. Of course, going from the initial benzene to my sigma complex is steep endothermic. It's going to require quite a bit of energy of activation. It cannot happen unless we have a super electrophile. And then re-aromatize, and of course, will drop down the energy again. Of course, this is your rate determining step, needless to say, forming the sigma complex. All right, again, alkenes can give you an addition reaction. Benzene will not undergo an addition reaction. With a superelectrophile, it will undergo a substitution reaction. That's never really beneficial. Chlorination, similar to bromination. Chlorine, typically, we try to match these to these. So bromine with ferric bromide, chlorine with aluminum hexafluoride, just so that we don't end up exchanging with halogen. But it's the same issue. Iodination, you kind of need to generate this positive iodide in situ with some iodine and nitric acid that will generate this in situ. But effectively, the reaction once you have this is the same. Sulfur trioxide is a gas. You can write it like this, or you could write resonance structure. Clearly, your sulfur is positive, while the oxygen share the negative charge. Sulfur trioxide is a powerful electrophile, which your benzene ring can attack. The positive sulfur, form this sigma complex, something comes, some base solvent comes along, and we re-aromatize. This can or not pick up a hydrogen, but this is a sulfonic acid. Sulfonic acids are some of the strongest acids ever. Stronger than sulfuric acid, right? Because if you put a negative charge here, you not only have all of this stabilization, but you also have the benzene ring on the other side. So this is an extremely powerful acid.
How do you get it at the end though?
This is
Yeah, how do you get that big?
water, you
Oh,
put
so
some
you just
hydrogen,
punch
like
it
any
down.
carboxylic acid or anything like that. You know, it's an acid, so it will exist in certain equilibria with water, part of it protonated, part of it as a carboxylic ion, well, the sulfate ion in this case. But there's an equilibrium between these two. This is actually a reversible reaction. So depending on how much of this you have, how much of the byproducts you have, you could take this and force it to break apart again. This is an equilibrium. And the show I'm here. Nitration of benzene. So the reagents are sulfuric acid and nitric acid. None of those two acids do you any favor if you spill them on yourself, but the mixture of the two is even worse. So one in here is acting as an acid and one is acting as a base. Which is which? This is my acid. This is my base. You don't typically think of nitric acid as a base, but in this case it is acting as a base, picking up a hydrogen from sulfuric acid and generating this very unstable molecule. Your water is now a good leading group, so that bond will break. We will give electrons to the oxygen that desperately wants them, and be left with this nitronium ion. with a positive charge on the nitrogen. That is a super electrophile, which your benzene ring can then attack. So you have nitric acid, sulfuric acid, and benzene. Oh, let's do it together. It is a nasty reaction. Dangerous reaction is the word I'm trying to use. Okay, so your benzene then attacks the nitronium ion and forms your sigma complex. We lose the hydrogen, re-aromatize the ring, and now you have nitrobenzene. And if you add 3 of these nitro groups, you have tri-nitrobenzene, or nitroglycerin, or stuff like that. Very explosive. Not good. Okay, well, nitroglycerin rather than using benzene and using glycerin, but similar kind of thing, not a good combination. Anyway, we'll get to alkylation in a second, but let me first introduce the idea of, this is just introducing one substitute. We could introduce a second substitute, and a third one. But where? Relative to the first substitute. If my first substitute is of carbon number 1, is it going to be of carbon number 2, or 3, or 4? Is it going to be ortho, meta, or para to the first substitute? So, that depends on the nature of your substitute. So let's look at the nature of the first substitute. If your first substituent is electron donating, so electron donors, there's 2 types of electron donors. You could have something like an ethoxy substituent, where this can donate electrons through the pi system. Right, and we can write all sorts of resonance structures here. So this is what we call a pi donor. We are involving those p orbitals that are laterally overlapping, and through the pi system, we are donating electrons. Right, so we could write this, then we could write this, or we could write this, that the negative charge here, the nucleophilic carbon in my benzene ring, is in the ortho and para positions. Compared to benzene, these are more nucleophilic than benzene because the oxygen is shoving electron density into the ring and making it more nucleophilic. So, first of all, we call this an activator because it is activating the ring, making it, the benzene ring is more nucleophilic than before. More nucleophilic than in anisole than in pure benzene. Okay? Anisole. So we call that an activator.
Every time I have the activator, does it mean that position or confirm?
So not only is this an activator, but it specifically activates the ortho and para position. So in this case, we would call this an ortho-para activator. Which means that when I put anisole in the presence of a superelectrophile, nitronium ion, whatever, it's going to be the ortho-para positions that will selectively react. So if I put anisole with, let's say, some nitric and sulfuric acid, I will end up with ortho and para substitution. Obviously this one as well, but that would be the same molecule. But no meta, or virtually no meta. So we say this is an ortho-para. An activator because this reaction occurs faster than if I just had benzene reaction with nitric acid. Right? It's that this is faster than this reaction. So this is what we call this an activator. But the fact that we go in these particular positions is what makes it an ortho-para activator. Okay, now, this was a pi donor. It is possible to have a sigma donor. That is, this methyl group cannot donate electrons to the ring through pi orbitals, doesn't have any pi orbitals available. But it can push these two electrons towards the ring. So alkyl groups are sigma donors. And again, that means they're going to be ortho-para activators. Not as good as a methoxy group, but ortho-para activators say. Okay? Now,
so you're talking about this is the covalent bond that's attached to the C towards the benzene?
so we're sharing two electrons, right? Those two electrons can be shared equally or unequally. So between two carbons, you would expect these two electrons to be shared equally, right? But if this is an electron donor, these two electrons are being shared unequally. So they're closer to the benzene ring than they are to the methyl, making the benzene ring inherently more electron rich.
Because electron density, right? Electron density.
This has to do with your ring, because the pi electrons can form temporary dipoles, which are a little bit more pronounced than those of the methyl group. So there's a difference between these two entities. It so happens that methyl groups are going to end up giving more electron density to the ring by whatever mechanism. It's not nearly as strong as the one through the pi system, but there is a net effect of alkyl groups being electron donors. So again, these are having alkyl groups are orthopara directors, and they are also activators. So when do we get meta? All right, so let's say that I put a nitro group initially. A nitro group looks like this. Would this be an electron donor to the ring or an electron withdrawing group? Right. I could draw this resonance structure. And I could draw this resonance structure. And I could draw this resonance structure. Now, remember, this reaction we need the benzene ring to be a nucleophile. So, when I'm giving electrons to my ring, your electron donating groups, whether through the pi or the sigma system, are activators of the ring because they're making the ring more nucleophilic. So this ring will react faster than benzene. When I'm taking electrons away from the ring, I'm making this less reactive than benzene. So electron withdrawing groups are deactivators, meaning less reactive. When the ring has a deactivator, the ring becomes less reactive than benzene. Okay, so let's put it that way. Ring plus deactivator is less reactive than plain benzene. So electron withdrawing groups like a nitro group or a carboxylic acid, anything that has something double bond oxygen or something triple bond nitrogen, like electron withdrawing groups are going to be, you know, a nitro group, a carboxylic acid group or ester, nitrile, you know, that type of thing are all going to be electron withdrawing groups. So this reaction is going to be very sluggish. It's going to react very slowly. And I'm deactivating the ring. But I'm particularly deactivating the ring at the ortho-para positions, which means my meta positions are a little bit more active than the ortho-para. Not a whole lot, but a little bit more. So because my ring needs to act as a nucleophile, it will preferentially attack at the meta positions, because the orthopara have been specifically deactivated. Those are the positive ones. So if I start with a deactivating group, and now I try to brominate, I will selectively brominate at the para position, at the meta position, because it's less deactivated. Okay? So you have activators and deactivators. You have orthopara directors or meta directors. Now, halogens are weird in that a halogen is electronegative. So inductively, it withdraws electron density from the ring. So a halogen is a deactivator. But a halogen can also donate electron density to the pi system. So it is a deactivator of the ring that is an orthopara director. Because it's selectively making your orthopara positions more reactive through the pi system. But inductively, it's withdrawing electron density. And so they're weird in that most activators are orthopara directors, most deactivators are meta directors, but this is somewhere in between. I'm a deactivator but orthopara director. And that is true for all halogens. So your summary for all of that is here. So, as far as your activators, orthopara directors, you can have pi donors, oxygen, nitrogen, sulfur with a pair of electrons that we can pump into the ring, or sigma donors, your alkyl groups of benzene. Your deactivators, which are meta directors, have a carbonyl bond oxygen, aldehydes, ketones, carboxylic acids, esters, or a carbon triple bond nitrogen, or a nitrogen double bond oxygen, any one of those things. And then there's the weird in between, where I'm a deactivator, but orthopara director. And those are your halogens. Okay? So this inherently gives you the final story. So when you're synthesizing molecules, a benzene that has multiple substituents, you need to plan. Because if I want these two substituents, let's say para, to each other, the first substituent that I introduce should be an orthopara director, because I want the second group to end up para. If I wanted meta, the first substituent that I introduce should be a meta director, or something that I can then convert into a meta director, or something that I can convert to an orthopara director, okay, before I do the next step. So I need to plan what to put first, second, third. Okay? Now, deactivating group means your benzene ring now reacts slower. So we also need to consider that. In a competition, something with an active group will react a heck of a lot faster than something with a deactivating group. So that's other things that we're going to need to consider on this list. But Try to keep that straight because it's what we're going to use to plan synthesis of benzene-containing compounds. Okay? So some of the things that I went over, showing all of your documents and whatever. This is also summarizing your activators, meaning obviously your pi, the ones that can donate to the pi system are going to be stronger activators than those that can only donate to the sigma system. So, there's a ranking in your activators. Something with a negative charge is going to be a stronger electron donating group than something without the negative charge. Now, some of these things are common sense. But that would be your ranking in terms of how activating a group is. And then deactivators, something like having a nitro group will make this benzene react 100,000 times slower than plain benzene. And that's because you're deactivating certain positions more. The general idea is when you're comparing benzene versus nitrobenzene, your benzene is inherently more stable because we're not deactivating, we don't have positive charge. So this energy of activation is lower, so I'm going to form product faster. That's why your benzene reacts faster than these guys. And the opposite is true when you have an activator. The activator is making it more stable than the benzene, and then the one with the activating group is going to react faster than benzene. Okay? Let's leave this here. We're going to start next time looking at introducing that second or third substituent and how do I plan things. Okay? We're going to do that on Thursday. And then